Okay, so one more lecture on gears, probably be doing one more example. So here's an example of a torque converter. I posted a link to a nice video that explains it far better than I can reasonably do so. Because of course, watching these things and watching diagrams in action and animations is very helpful for this. So these are what help you disconnect the input shaft from the user so that you can idle to a large degree. So useful in a lot of applications are helical gears. They'll be uh, put inside the transmission, but the helical gears are going to be, they're looking something like this, right? So the idea is that by cutting our teeth at an angle, when they turn together, they mesh smoother. So they're more they generate less noise, and they also kind of share the load amongst the teeth better, so that they can kind of be stronger. So for a bit of a diagram, so we're gonna be cutting it at a particular angle. We're denoting that by our psi here. So psi is our helix angle. Obviously, for spur gears is 0. So looking at the two different cross sections, so we've got the cross section. So this one is what we would get if if we slice. This is the section RR, so it's associated with this line right here. So if we just slice the thing down the side and we're looking at the cross section, and we'd see this pressure angle and this pitch measured in the plane of rotation. And then, of course, obviously, if we were looking at side, we wouldn't just see the, these teeth here. We'd, the rest of the tooth would kind of be shown here. And obviously, this is also circular, but anyways. So yeah, that. So if we're looking at the tooth like that, then we're going to get a particular pressure angle and a particular pitch. But if we're measuring it, kind of looking at it from an angle, so if we're looking at it from this direction, we might be seeing something like this. So we're going to have a different pressure angle and a different pitch. That's measured normal to the teeth. And this is essentially the pressure angle and pitch that would be associated with the process that was used to cut the teeth. So if you're using a hob cutter or some sort of gear forming that has the shape of the tooth built in, they're going to be cutting. They're going to be cutting. It's going to be cutting going back and forth this way, right? So the shaping of the teeth is going to happen that way, and the geometry that it's cutting out is going to be based upon this. So when we kind of compare those two, the module of the normal module, so that this one here, measured normal to the tooth, is going to be the module here, or module here, measured from here to here, from here to here, however whichever points you want to measure it from, times the cosine of the psi. And then relating the angles in question, the tangent of this pressure angle here is going to be equal to the tangent of this pressure angle times the cosine of the helix angle. And then if we're working in terms of diametrical pitch, we're working in imperial. Just the Pn is equal to P divided by the P times the cosine of the psi. Sorry, divided by the cosine of the psi. Did I say multiplied? Whatever. P divided by the cosine of the psi. So again, this P would be based upon this measurement here, just how many teeth per inch you get there. So also one thing, so the point is to have kind of progressive meshing of the teeth as they come into contact. You're not, so what you want to have is you want to have a certain amount of overlap between the teeth in question. So basically, if we measure from this point here to this point here, from like the top of one tooth to the top of the other tooth, and then follow this line along till it intersects where, the position here. I'm going to call that PA. So what we want is we want for that PA to be less than the width of the of the gear. Because if we do that, then basically, if this thing is less than that amount, then we're going to have that thing coming into contact. We're gonna have the two teeth kind of coming into contact with one another. And I just wanted to specify, like when we're looking down here, the different colors, like this is like the top, and this is the bottom, top, bottom, and then this section here, that section there, and the is just the kind of the slanted portion. So anyways, so typically speaking, you usually want the width of your gear to be at least over 1.15 times that PA. Over 2 is fairly common as well. So again, that just primarily depends upon what our module here is and what the helix angle is. So as with spur gears, the force between the mating teeth is always perpendicular to the tooth surface. That's certainly just as per spur gears, as per any surface coming into contact with one another where we're neglecting friction, or where friction is minimal. If I press against, something, the contact pressure is always going to be perpendicular to those mating surfaces. So it's the normal plane profile that determines the strength of the gear. Because again, when we just look back here, this is the surface that's going to be coming into contact with the mating surface of the other tooth, right? So it's this geometry here that determines how strong we are, not up here. Obviously, this geometry combined with the helix angle determines what this geometry down here is. But it's the normal plane profile that determines our strength. The other thing that comes into play here is that since we have the forces that are perpendicular to the tooth surface, and that tooth surface is no longer parallel with the axis of rotation, now we get an axial load that's introduced. So oftentimes that gets canceled out by having just kind of getting a pair of helix gears next to one another. That it might be the same gear, just kind of machined out of different parts. Machined separately, or it might be two gears next to one another that are mounted together. Either way works, as long as the angle is the same. Then you can get the axial loads that would otherwise be introduced canceling out one another. So like this one might have a tendency. This one, based upon the rotation, is going to have a tendency to push this way. This one's going to have a tendency to push that way. They just push against one another. So the strength of the gear teeth is based upon the profile when we're looking at it normal to the tooth. So basically, if we take our circular gear and look at it from a separate angle, what happens is we distort its shape. So we distort its shape into this ellipse structure here. And basically, kind of at the point where the tooth lies, that ellipse has kind of like an effective localized radius that is larger than its actual radius. So we call that the effective radius. So that's just equal to d divided by 2 times the cosine of phi squared. Sorry, psi squared, not phi squared. Psi squared. So we can also, so if the effective radius is larger, then kind of the effective number of teeth would be larger. So we can kind of pretend that the number of effective teeth that we'd have is larger based upon n divided by the cosine cubed of the psi. Kind of once we solve for that, the cube comes into play there when we're also plugging in our pn values there. So based upon that, we'll come back to that in a second. So we've got the helical gear, and again, when it's meshing with another gear, we're going to get our FT there. Again, that's what's transmitting our force. We've got our FR, radial, still happens, and then we've introduced this new force, the FA. So for strength analysis, we're still assuming that the FR and the FA are negligible. We're not worried about how they're really affecting the sorry, we're still assuming that the FR is negligible. The FT is what transmits our torque. The FA and the FT, they do combine together to give us the our the actual force on our gear tooth here. So we can adjust for that by essentially using a J value that is based upon that NE that we calculated earlier. So we're not using the J for the based upon the actual number of teeth. We're using the J based upon the number of effective teeth and then the pressure angle on our normal plane. So we can either try to figure that out kind of looking at the J chart from before, or we can go to this figure here in juveniles. The other thing that comes into play here is that our mounting factor gets dropped down to 0.93 of what the km would have otherwise been, and that's just because of the smoother loading of helical gears. It's less sensitive to mounting conditions. So this figure that I mentioned here, it's right here. So essentially, if we know what the helix angle is, and the we can read off what the J is based upon the helix angle and the number of teeth for the gear that we're talking about. And these are all based upon having a pressure angle, a normal pressure angle. Again, that's when we're looking kind of at the tooth straight on of 20 degrees. So essentially, kind of when we're using our hobs or what have you to cut our gears, we're still using the same profile. We're still using the same profile that we're cutting. We're just cutting it at an angle. Yeah. So So we take that geometry factor and then we adjust it by multiplying it by a factor that is based upon the number of teeth in the mating gear. So essentially when we saw the J chart, yeah, I'm sure you recall, here, I'm gonna move this to the side here. I'm sure you recall it kind of it did something like this and then split off into a bunch of different lines for the number of teeth that it was mating in. So that's kind of accounting for that. And again, this is if we're other than 75 teeth. If the mating gear has 75 teeth, then well, I guess they included that line. If the mating gear has 75 teeth, then the multiplier is 1. So that's for our bending stress here. That's for the stress. The strength portion doesn't change, so the strength still calculated the same way. For our surface fatigue stress, it's not as bad because again the stress is spread over a larger area due to the slant, and again also the fact that we have the gears meshing together progressively. So there's always going to be at least, there's going to be more than one gear in contact, even when the even like if when one gear is in contact at the pitch surface, so which is basically the worst case scenario when for contact stress, that's where it's the worst. There's still at least another gear tooth into contact, so we're still going to get a bit of a sharing of the load. So again, that's going to be kind of the same as we just calculated. These things are calculated. That's calculated the same as for the spur gears. The factor that we throw in here is our helix angle, cosine of the helix angle, and the contact ratio. So bevel gears. Bevel gears are fun too. I'll be throwing a few videos in Moodle to kind of show you how these work. But bevel gears are basically gears that are, they're essentially, well, let me think. If we're kind of looking at the cross section of one of these, then essentially we kind of get, you can get like the teeth sticking out like this, and then it rotates kind of around this axis up here. So you can get them straight cut, you can spiral cut. So essentially, the idea is that the two bevel gears will kind of be coming together such that they're kind of the cones that form the kind of the surface of well, the kind of, I guess, the pitch surface, I suppose, come together at a point. I also got Hypoid Gears. Again, good video that'll be thrown in Moodle to show you there. These ones can actually allow for rotation of one of the gears kind of about the axis of the other. So yeah, essentially, we got a pitch cone here. So instead of a pitch circle, we've got a pitch cone, and then the teeth kind of meet in the where the two pitch cones start or come together. So of course, the primary purpose of a bevel gear is that you're also going to be changing the axis of the direction of rotation. So we're changing directions here, and then it's going to be about here. So as opposed, like there are spur gears and our helix gears, they still transfer, they offset the axis, but it's still turning in the same. It's turning parallel there. So bevel gears will allow us to change the direction of the axis of rotation. Worm gears also allow that. So worm gears, you typically speaking, yeah, you're going to have the worm that is the uh, that is our input, and then you're going to have the worm wheel here that's our output. Doesn't really work the other way around. If you try to just rotate this and expect your worm to turn, not going to really work well. Typically speaking, uh, the friction would be too high for that to work. But um, worm gears are good because worm gears can be good because you can get exceptionally high uh, gear ratios with worm gears. Uh, Typically speaking, they're not the most efficient, but again, that might not be too critical, especially if we're talking relatively low power situations. But yeah, that we can get good, very high gear ratios. And yeah, again, I'll throw another video to kind of see one of those in action. And that is it for kind of the theory for what I'm going to do. Again, analyzing the stress of worm gears and bevel gears is fairly similar to kind of what we saw for spur and helical gears. So I'm not going to, I expect you guys to by now have gotten to the point where if you need to be able to do that analysis, you can figure it out from your textbook.